Alrighty, we are once again adding to our concept map, adding lectures 15 and 16, I believe, on distributed load and moment of inertia, question mark, yeah. Okay, let's start with distributed load. I'm gonna put it right here because it's an extension of equivalent force systems, kind of, yeah. Distributed load. Okay. What this means is, oh, I don't like that. Force spread over load, also kind of length or area or volume. So what are some real life examples? We talked about weight on a beam, snow on a roof, okay. Let's draw a line connecting this to equivalent force systems. Good thing that I've already put them very closely together. Okay. I'm gonna die. Wait. Okay. I'm okay. We can write the magnitude as R equals the integral of W x dx. And for simple shapes, R is area under the load diagram. And this, of course, acts at the centroid of the load diagram. In this way, this is related to how before we would replace like many forces with one resultant, which is exactly kind of what distributed load idea is doing. Taking the whole like load and replacing it with magnitude at a certain point. And how do we determine the location of the resultant? Let me location. That's given by xr equals integral xw x dx w x dx. And this can be interpreted as the first moment of load distribution we'll notice this is kind of the same structure as our centroid equations, which is why I put them kind of close together. We'll often break these loads into shapes like wait, let me write that down. Like rectangles, triangles, polygons, trapezoids. And the general solving steps will be similar to composite centroids, which is another reason they're very, of course, centroid and moment of inertia are very, what am I talking about? Centroid and distributed load are very closely connected. So find the area. Actually, yeah. Each we'll want to find the centroid location, and then some of the moments. Guys. So let's think of some real life examples. Distributed loads are common in things like I think we talked about beams, bridges, structures. Which kind of relates to truss analysis. Because bridges and shit. Oh, and stuff. Where I put the trusses? They're up there. Okay, it's kind of far. But I'm gonna draw a line anyway. Alright. So let's move on to moment of inertia. I want to keep it near centroid, so I'm gonna keep it put it right down here next to where I put distributed load. What color? It's low-key giving dark blue to me. Alright. Moment of inertia. Oh wow, it's kind of small. Oh wow. So moment of inertia, by definition, is the resistance to bending and rotation forward. Oh. This means this is represented by I, means less deflection, lower bending stress. Oh, that's getting kind of close. Let me move that. Move the whole thing actually. And our equations for this, write it bold, I x is equal to the integral of y squared dA. I y is equal to the integral of x squared dA. Okay. And then we also have, I'm gonna cry. Okay. J O is equal to the integral of r squared dA equals, which is equal to the 2 before added, ix plus I y got it on recording, but okay. The key idea is that in an area, an area farther from the axis increases I. This is similar where did I put moment? Can relate this, where did I put it? It's right there, it's really close, that's convenient. Of course, it's close to moment because moment and inertia, of course, they're related. And both of these depend on distance from the axis. At moment of inertia, okay, when we're determining it by direct integration, can't have nothing in this house. Okay. It's important to choose a coordinate system. Defined our differential element dA. Express it as distance from the axis to the axis. Okay. And set the limits and integrate and so typically if we're integrating, if we want to use horizontal strips, we're going to find Ix. And if we're looking for vertical strips, we're going to use Iy. This is the same integration process that is used in calculating centroids and distributed loads. But we've also got a more simple method of composite areas, bodies. In this case, we will break the shape into simple areas. Back still recording, into simple areas. Compute each individual inertia. And sum the contributions. Which uses the same logic as composite centroids, which you've already connected to, but also equivalent force systems. When, and then this brings us to parallel axis theorem. Which is used when the axis is not through the centroid. We can use the equations. Ix equals I bar x plus AD squared, and Iy equals I bar y plus AD squared. Where I is our centroidal moment of inertia, and d is the distance between axes. So this would make sense that moving material away from the centroid would increase I. Okay, I think that's looking pretty good for lecture 15 and 16. Look at our concept map, that's looking pretty good.